Welcome to this explainer. Today, we're jumping straight into a highly analytical breakdown of the very foundation of modern power electronics. We're going to strip away the complexities of dynamic operation to focus entirely on the foundational thermodynamics, the underlying physics that literally dictate whether a system thrives or just burns out. So if you engineer, design, or just want to deeply understand the physics governing everything from massive data centers to electric vehicles, you are absolutely in the right place. Here is the roadmap for our explainer today. First, the illusion of ideality. Second, defining the steady state. Third, the physics of conduction loss. Fourth, the thermal feedback loop. And finally, number 5, engineering high-efficiency inverters. All right, let's get to work. Section 1, the illusion of ideality, and breaking down the 100% efficiency myth. Okay, let's dive right into this by addressing a concept that, frankly, only exists in textbooks: the ideal circuit. Before we can start engineering real-world solutions, we absolutely have to shatter this myth of a perfectly lossless system. Sure, in a purely theoretical setup, efficiency is a perfect 100%. Conductors have zero resistance, and electronic switches have zero voltage drop. But as we all know, physical reality is way less forgiving. In our real-world systems, we're constantly fighting parasitic resistances and those inevitable voltage drops across our semiconductors. Actual efficiency is literally always less than 100%, and that missing percentage doesn't just magically vanish. It's converted entirely into heat, and heat is the absolute enemy of electronics. Section 2, defining the steady state, the baseline for our analysis. So to truly grasp where and how this heat is being generated, we first need to establish a solid baseline. Before we even think about tackling complex dynamic scenarios, let's define the steady state precisely. We're talking about an operating condition completely devoid of rapid switching. Switching transients are entirely absent here, and our electrical quantities are constant, or at most varying very slowly. For our MOSFETs, this means the device is in a permanently on state. It's a continuous, unbroken channel of conduction. To really ground this theory, this QSpice simulation schematic beautifully illustrates our baseline in action. Notice the UJ3C series MOSFET on the right side there? It's being kept constantly on by a steady DC source with absolutely zero rapid toggling of the gate. By intentionally isolating the system from dynamic switching losses, any inefficiency we observe here is purely a structural characteristic of the circuit and the component itself. Section 3, the physics of conduction loss and the mathematics of dissipation. Now, with switching losses completely eliminated from our equation, we're face to face with the absolutely dominant thermal factor in this permanently on-state regime: conduction loss. And here is the critical physics relationship every single engineer must respect. The power dissipated equals the square of the current multiplied by the drain to source on resistance, or RDS on. I want you to let that sink in for a moment. Because the current is squared, simply increasing your load current produces a massive quadratic increase in heat dissipation. This is the unavoidable mathematical reality of conduction loss. Now, what's really fascinating about this slide is how perfectly the empirical data backs up that equation across some pretty extreme conditions, from negative 20 degrees Celsius all the way up to a blistering 170 degrees. If you look at the top graph in red, as the temperature rises, RDS on increases almost linearly. Now follow that down to the blue graph. Because resistance is climbing, the power dissipated climbs right along with it. And consequently, looking at the green line at the bottom, your overall system efficiency steadily drops. Which brings us to Section 4, the thermal feedback loop, a vicious cycle. And this brilliantly illustrates the real danger. What those stacked charts just revealed isn't merely static data. It's a dynamic, physical consequence of our math. This diagram perfectly captures the dangerous self-heating mechanism at play here. It's this closed, self-reinforcing circle where an initial rise in temperature doesn't just stop there. It acts as a catalyst, driving rapid changes throughout the entire semiconductor. Let's walk through this chain reaction step by step because it's absolutely crucial. First up, the ambient or operating temperature increases. Because of the inherent physical properties of the semiconductor material, this causes the RDS on to increase. With a higher resistance blocking the path, our conduction losses inevitably rise. Those losses are then released as energy, meaning power dissipation increases, which becomes heat. And that brings us right back to the top of the chain, further driving up the temperature, and the whole self-heating cycle repeats. Without proper heat sinks and a smart thermal layout, this loop will severely degrade the long-term reliability of your device. Finally, Section 5,
engineering high-efficiency inverters and the golden rule.
So the crucial point is this. We've identified the core problem, conduction loss driving a massive thermal feedback loop. But how do we pivot to a solution? Well, we have to understand the physical component limits we're working with. 80 milliohms. This is the typical on-resistance value for the specific MOSFET we used in our earlier simulation. And while advanced materials are constantly pushing this number lower, 80 milliohms as a physical reality in that specific circuit. You simply cannot engineer away this baseline resistance. You have to design around it. Which leads us directly to an ironclad law of power engineering. Because conduction loss completely dominates the steady state, and because those losses increase quadratically with current, RDS-on is the absolute first parameter a designer must analyze when engineering high-efficiency inverters and power supplies. It completely dictates your thermal management. It dictates your power density. If you get the RDS-on wrong in the steady state, your design is fundamentally compromised before you even introduce the complexities of dynamic switching. So, I'll leave you with this provocative thought. Knowing how rapidly conduction losses can literally spiral out of control, can you actually afford to neglect steady-state analysis and risk structural inefficiencies in your next design? You have to understand the baseline, control those thermal loops, and always remember, compute before building with Engineering World Company.